Welcome to IMAGO Tutorials. This tutorial shows how to configure a Microsoft Visual Studio project to conveniently program the VisionSensor PV remotely from a Windows-based PC. Visual Studio is a powerful IDE, which includes code editing with automatic code completion, as well as a convenient user-friendly debugger. Among other possibilities, Visual Studio supports building and running C++-based programs onto remote Linux devices. Let's start by opening Visual Studio 2017. In this tutorial, we are using version 15.7.6. Create a new Visual Studio project by hitting File, New, Project. Select Visual C++, Cross-Platform Linux, Empty Linux project to create a new Linux application. If you don't see this option, check your Visual Studio installation. The Linux development with C++ toolset must be enabled while installing Visual Studio. Pick a name for the project, like Test in this example, and finally hit OK to confirm the settings. After the creation, the new Linux project appears in the Solution Explorer window on the right. Before proceeding, we must specify the network details of the remote Linux device, in this case the VisionSensor, to allow Visual Studio to connect and exchange data with it. Open an SSH connection to the VisionSensor and run ifconfig to print out its network configuration. To learn how to connect to the VisionSensor, please check the tutorial in the link below. Copy the IP address by simply selecting it. Then go back to Visual Studio and select Tools Options from the main menu. Select Cross-Platform and press the button Add to add a new SSH connection to the remote device. Paste the IP address of the VisionSensor by pressing Ctrl key and V inside the hostname field. Specify the username root and the device's password, which is Vision by default. Finally, hit Connect to add this new connection. Visual Studio attempts to establish an SSH connection with the provided IP address and credentials. If successful, it creates a local copy of the headers and other code definitions of the remote Linux system. These are mainly used by Visual Studio to enable code completion and improve the debugging experience. This operation may take a couple of seconds. Once done, press the button OK. Now that the connection details to the VisionSensor have been specified, the project properties have also been automatically updated. To check this, open the property pages of the project by pressing the spanner symbol. In the General Configuration Properties Remote Build Machine field, you can visualize the connection details and eventually choose the one which is needed. Let's have a look at the remaining options. The field Remote Build Root Directory specifies the remote root directory where the Visual Studio projects will be copied. In this case, /projects, where the / stands for the Linux user home directory. Since we have configured the connection using the login root, the / translates to /root. The specific directory of our test project will be copied, compiled, and run on the Linux machine at the location specified by Remote Build Project Directory, i.e. /projects/test in our case. In the Configuration Type field, it's possible to choose the output of the project building, either a dynamic library, a static library, a simple application, or even makefile. Notice that only Linux output formats are available. We are interested in building an application, so we leave the field value as default. Finally, hit OK to confirm the settings. At this point, we have properly configured the Visual Studio project to build and execute on the remote VisionSensor with the given connection details. We are still missing a C++ code to test on. Let's download the FrameGrabber example code, which is stored on the VisionSensor's examples directory together with the IMAGO SDK. Open the project directory where the Visual Studio files are stored and grab the MobaXterm terminal with an established connection to the VisionSensor. Change the terminal directory to /opt/imago-technologies/examples/fgexample_linux to access the relative files. The SFTP browser on the left should update its content to reflect the content of the selected folder. Please make sure the checkbox on the bottom is enabled to follow the terminal folder. Select the content of this example folder, then drag and drop it into the local project folder Test. Double-click the Test folder to check its content and make sure the source SRC folder has been copied from the VisionSensor. Now we include the downloaded C++ code in the Visual Studio project by first adding a new so-called filter into the test project solution and then renaming it source files. This will be the solution internal directory where the source.cpp files are stored. For completeness, we also add another internal filter in the project to hold the C++ header files as well, i.e. those with the .h file extension. We add the C++ example code we downloaded from the VisionSensor by right-clicking on the Source Files filter, Add Existing Item. Then, from the pop-up window showing by default the root directory of the test project, we move into the src directory where the example sources are stored. Select the only file main.cpp and press Add to add it into the source files of the project. Let's visualize the content of the main.cpp file, which appeared inside the source files collection by double-clicking on it. Before being able to build this example code, we need to update the project properties to add the IMAGO SDK include and libs directories. Make sure the test project is selected, then open the property pages by pressing the spanner symbol on the bottom right. Access the C subpages and select the general options. Here we need to update the additional include directories to add the IMAGO SDK headers. Once more, grab the MobiXterm terminal and move from the example directory to the root SDK directory by running cd ... twice. From the SDK directory, run cd include / to move to the include directory and inspect its content with ls. This directory contains two header files with important interface functionalities to allow handling the VisionSensor. The vib_interface.h, which is an abbreviation for VisionBox interface, contains a platform-independent API to access the hardware functionalities of the VisionSensor. The additional library file fg_camerainterface.h, standing for Frame Grabber Camera Interface, contains a camera abstraction interface to mainly handle image acquisition from the initialization of the camera buffers to the actual image grabbing. Copy the entire path to these interfaces by selecting and pasting it onto the additional include directories in the Visual Studio property pages. Remember to separate this path from the others already present in the field with a semicolon. If you have accidentally replaced the default paths, press Cancel on the bottom right of the window to repristinate the original values. Next, access the Linkers subpages and select the General options. To allow proper linking of the code, we need to update the additional library directories with the IMAGO SDK libs. Open MobiXterm. Move one folder up by running cd ... and reach the SDK lib / directory. Inspect its contents with ls. This folder includes the necessary library for properly linking SDK-based programs on the VisionSensor. Copy the entire path to the IMAGO SDK libs by selecting it and paste it onto the additional library directories of the project. Begin the path with a semicolon to separate from the original paths as before. The remote SDK library directory contains mainly two dynamic library files, the libfgcamera32.so and the libvibinterface32.so. They are both stored as .so, which means shared object files, and must be linked to the main program at runtime. Select Input of the linker property pages of the Visual Studio project and update the library dependencies fields with these two library files, separated by a semicolon. Avoid entering the prefixes lib as well as the extensions .so, as these are filled in automatically by Visual Studio. Once done, press Apply followed by OK to confirm the new settings. Before starting the program, make sure the selected running platform in the combo box on the top is set to ARM. Now we can hit the green play button to finally run the example program. After initially validating the architecture and copying the sources remotely to the Vision Sensor, Visual Studio starts the remote compilation of the sources and linking. All these operations are stated one after the other in the output window on the bottom left. In the case of an error, the execution stops with a description of the error, which must be fixed before attempting to run the program again. In case of success, the Linux console window appears in the bottom right, showing the standard output messages which are printed by the program. The initial warning line produced by GDB is harmless and can be ignored in this context. The program prints out the frame grabber camera version, in our case version 1.1.1.1, and then grabs a single image in free run mode, outputting its data pointer and its number. Notice that the grabbed image number is stored internally and increases every time the program is restarted. Rebooting the Vision Sensor resets the counter to 0. Place the cursor right under the last printed line and click to set its position. Then press any key as stated and the key Enter to exit. By now, we have successfully run a Visual Studio program inside the remote Vision Sensor. Notice that the program successfully compiled and linked on the remote machine, although Visual Studio was unable to recognize some symbols related to the frame grabber camera interface. This is because the corresponding include files are located on the remote Linux machine on the Vision Sensor and locally unknown. Let's have a look at the missing include file stored on the Vision Sensor. Grab the MobiXterm connection to the Vision Sensor, clear the previously run commands for clarity, and move to the remote SDK include folder /opt/imago technologies /SDK/include. Open the local Visual Studio project directory test and create a new folder by right-clicking on an empty space inside the folder. Rename the folder to remote_include. This folder, as the name says, will hold the remote include files, with the only intent to let Visual Studio recognize those missing symbols and therefore improve the debugging experience. Double-click on remote_include to open it. Select the two SDK include files from the SFTP browser of MobiXterm, then drag and drop them into the local remote_include directory. Now we can update the project configuration to let Visual Studio locate these additional include files. Select the test project and open the property pages using the spanner symbol. Here select the C++ page and click on the general properties. Update the additional include directories by adding the following command at the end. This will let Visual Studio know where to look for additional includes. After confirming with OK, all the previously unrecognized symbols related to the frame grabber camera interface are successfully found by Visual Studio. To conclude this tutorial, let's make a small test. As explained, Visual Studio copies, builds, and executes Linux programs directly on the remote Linux device. Let's locate the generated executable and try to execute it directly from the command line. Open MobiXterm, clear the shell for clarity, and move to the home root's home directory by simply typing cd. Then move to the only remote projects folder /projects/test. By inspecting its content with ls, we find the copied source file main.cpp as well as two additional folders, the bin folder containing the executable and the obj folder used for remote building. From there, move to the bin/arm/debug directory to discover the executable Test.out. Execute the program from the command line by typing ./test.out. Notice that the program outputs the same strings we got before from Visual Studio, stating the frame grabber camera version, image pointer, and number. As before, press any key to end the program. Then press Enter to confirm. In this tutorial, we have explained how to configure a Visual Studio project to build and run C++ programs on the VisionSensor PV. We have explained how to configure the project to properly link to the IMAGO SDK headers and libraries and successfully run the frame grabber example remotely. To see more video tutorials, check out our channel. Thank you for watching.